So welcome back, everybody. And we hope you had a great weekend. So the topic this week is a kind of continuation of what we did last week. And we are going to link things up with a solution of the homework set, which you have for Friday. And then you will see that many of the exercises we're going to look at, they will also be the exercises in the second homework set. They can actually be, some of the material can be reused in the third homework set. So what I want to do now is, in the lectures now, is to try to catch many birds with just one stone. So we go through examples of simple force problems, how we can solve them numerically, and how they link up with the homework problems. So on Monday and Wednesday, the main topics actually going to be, so let me just bring this back again here. So when we look at the topics for this week, we are going to look at the various forces and types of problems. You will always see the kind of recommended reading. So we are following pretty closely Taylor's textbook. So you will find many of the homeworks and many of the things we discussed during the lectures explained pretty well and in depth in Taylor's textbook. So also on Wednesday, we will continue with many of these models, and we will also discuss a little bit more in depth exercises 5 and 6, because these exercises deal with a way we represent two-dimensional objects when we want to program them. And you can obviously program the velocity in the X and the Y direction just as individual arrays, but you can actually write a program which is much more compact. So we are going to look at both ways of doing it. You won't be penalized for not doing the fancy way or the more compact way. So we are not looking after the way you program, but we're looking after your physics insights. But sometimes it can be easier to program some quantities if we can make use of the fact that we have the possibility to represent two-dimensional and three-dimensional quantities in just one single line of program. So the topic for this week should be pretty well set. What I want to do now is to bring you a little bit back to where we were last week. And we are going to look at how we would program that specific problem. And then we are going to look at a similar problem, but where the drag force is now only proportional to the velocity, and how we could program that problem with two-dimensional objects. This is actually the topic in exercise 6 this week, and some of you may already have seen that. If you haven't seen it, we are going to discuss this week together with the different examples of applications of forces. So that's basically the program for the week here. Let's go a little bit back to where we were last week. So one of the things we looked at last week was a falling object, but in a gravitational field, but it was in one dimension. However, what we did was to add a drag force. Now, if this object is falling pretty fast, what you would see then is that this drag force can be modeled as the velocity squared. So I have a small video there which you can look at, and how you can actually develop some intuitive arguments on how you can actually study and get this expression for the drag force. This is a model which we make. Now, what that means, and this is what we did last week, was to rewrite the differential equations. So I'm just repeating a little bit where we ended last week. And then we could integrate up, because we could actually do this analytically. And this is a typical equation where we can separate the velocity in the y direction and time. And then we can, with this technique of separation of variables, we can get a right-hand side, which depends only on time, and the left-hand side, which depends only on the velocity. And then we can integrate up. And when we do that, if we can do it, that's obviously the thing we would do. Else, we would have to do it numerically. And you will see that in the numerical exercise for homework 3, we are not going to get an equation which can be solved analytically. So what we did last week was then to solve this problem. And after some integral manipulations here, we could then find that the velocity is given by the tan hyperbolicus times the gravitational constant times time divided by a constant. And then when we did that, we could then perform the same calculation for the position. And then we had analytical expressions for these quantities. This is extremely useful when we now are going to study this numerically. So the numerical study here is actually a what you might call a kind of overkill, because we have a nice analytical solution, but the numerical exercise here, doing it numerically, allows us to actually test our program and gain some confidence. So this is extremely useful to have analytical solutions, because they simply tell us that, okay, my numerics is functioning, I'm getting back the analytical solution, but we're also going to look at the numerical solution, because the numerical solution, you have to keep that in mind, is an approximation to a continuous problem. So in these calculations, we have assumed that time is a continuous variable. When you do an experiment, time will always be a discrete variable. But when we integrate now, we have made this assumption. When you do it numerically, you always get back to real life again, because then things are discrete. However, if you now don't want to run through all these kind of manipulations by paper and pencil, you also have symbolic Python. Some of you may be familiar with Mathematica. So when you are solving things here, and you are doing it by paper and pencil, you should feel free to solve it with symbolic packages. So if you don't want to do it by paper and pencil, you can always use SymPy or Mathematica to solve an integral. That's fully allowed when you do the exercises. We are not forcing you to use paper and pencil. You have to figure out which are the most relevant tools. And performing an integration is fun. It gives you this feeling of mastering something, but there is no deeper insight in it, right? It's like a tool. But it's useful to be able to do it, clearly. So we are not trying to denigrate the usefulness of mathematical operations here. Now, the thing we can do now is to start looking at how we program it. So if we go back to the previous slide here, what we had then is actually an expression for the acceleration. So if you look at this middle expression for the acceleration, this is the one you have to program. And that's where your program will start, by setting up or finding the expression for the acceleration. You found the forces. When you found the net forces, you divide by the mass which is involved, and then you have the acceleration. And this is the quantity you need to plug in to a numerical program. So when we do it numerically, we actually start with this expression for the acceleration, which you see here. So let's take a look at it and how we will do that. And then we are going to look at more examples. So let me just share the screen here again. So let's look up the Jupyter notebook. So this is the expression which we have seen. And if you now move down a little bit, so we have the expression for the acceleration, which you can see here. And that's a derivative of the velocity with respect to time. Now we skip the analytical part because we looked at that when we did the solution last week. But what we will do now when we prepare for the numerical solution is that we will define an initial position, which is this y0. So the object is still falling down in the y direction only, so one-dimensional problem. And then we need to fix the initial velocity. So this is something we have to give to the problem in order to find the solution. So what we did the week before last week was to perform a Taylor expansion. And in the Taylor expansion, what we would keep if we want to use the simplest possible method to find the solution is to keep only the first derivative with respect to velocity and with respect to the position. Now this is the acceleration, so we know the acceleration, and we can plug that into the code which we are going to write. We don't know the velocity. This is the quantity we want to find. So when we did this Taylor expansion, we skipped all terms which go like delta t squared. And then we ended up with something which looks like this. And then we skipped the delta t squared terms. And then we ended up with something which looks like this. So this will be the position in the next time step, the previous time step, and we start with the first time step, t0, where we know the solution. We need, I guess, we need an initial value for the velocity, and we know the acceleration. So that's the quantity we know, and we can fix delta t. So delta t, it's actually you who sets delta t when you're going to find the solution. And your results will depend on the value of delta t. That will be the resolution of your solution. And you will see that if delta t is very large, your solution may actually differ a lot from the analytical solution. So let's look at the code example, because the kind of code which you're going to see down here is something which is going to be pretty common for the rest of the semester. So the whole thing, when you have a numerical program, is you identifying the forces. And when you have identified the forces, you have the acceleration. And that's what you need to plug in to your program. So let's take a look at the way we will set it up. So one thing we can do is we can define delta t. So there's nothing which hinders us to do that. Or alternatively, I can actually define n. Here, I would now define the number of integration points as a function of the final time. So I take a ceiling, final time, delta t. So the ceiling function returns, this is something to keep in mind. It returns the smallest integer, which is not less than the input. So that means that if you have 21.15, what you get then is 22. If you have a ceiling of 21.75, it gives you 22. Then if you take the floor function, that actually gives you the smallest integer. So if you take 21.75, you get 21. So these are useful functions which you can use if you want to use them. This is just a quick reminder of some computational aspects. So what we would do next now is typically to initialize, what you could do is to initialize the number of integration points. You define a final time and an initial time, and then you can find delta t, defined as a function of so-called mesh point or integration points. This is another recipe. You can fix delta t, or you can fix the number of integration points. It's very much up to you to choose what kind of way you want to set up the arrays which contain positions, velocities, and accelerations. So then what happens next is that you can typically define the acceleration. Now you define an array, you initialize things with NumPy, and now you say that this is an array with 10 elements. So if we look at Euler's method, the first thing I've done here is to fix a constant. There are some basic things here which we don't need yet. So I'm fixing the acceleration, the gravitational constant. I'm fixing this constant d. I'm setting up my delta t. I set my final time. And then I'm also defining a scaling constant, as I did in the theoretical calculations. And then I'm setting up an array for time, acceleration, velocity, and position. And in this specific case, we know the analytic solution. So I want to compare my numerics with the analytical solution here. And we need now, this is very important, we need to define the initial conditions. That's a very important aspect, because without them, we don't know what the final solution should be like, right? So we would have an infinity of final solutions, but with the initial conditions, then we have defined exactly what kind of final solution we are looking after. So just keep this in mind, because when we can solve differential equations and find an analytical solution, but they will depend on constants which are undefined till we have specified the initial conditions. And now you see the thing you need to do now. So what I'm doing, I'm setting up a variable now, which goes up to the second last point. And then I set up an array with the acceleration. And my acceleration is now the velocity squared. And the velocity is a quantity which now is defined in terms of the initial velocity. So I start with initial velocity, and then I get the acceleration at the initial point. And then I continue like that, time step by time step. When I have that, as you see here, I have my y0, so and v0. So that means that when I start the counting here, I start with the first element, which is element 0. And then I have my acceleration at time 0. I could actually have put that one equal to minus g. I update the velocity, and this is Euler's method. And you see now, this is the thing you need to actually program if you have Euler's method. One line for the acceleration, and then you have the algorithm itself, which integrates up velocity and position. And in a certain sense, when you look at what you have here, it's what we are going to do throughout this course is a kind of repetition of what you see here. It may be in 2 dimensions, it may be in 3 dimensions, but the basic message, if you look at what you have here, this is the kind of recipe we are going to use again and again when we are going to integrate up equations. The only difference is that, like, this method, Euler's method, is a little bit unstable when you are integrating up over long times, and it doesn't conserve energy. But we can actually make some small adjustments to it, and then we can integrate it up and still conserve energy to a given precision defined by this delta t. So what you would see now is that I can proceed, I update time, and then I find the analytic solution, and this is the one I want to compare with. So I'm just punching in the analytical solution, and then I'm simply calculating the difference between my numeric solution and the analytic solution. And then I'm plotting things at the end. And you will see now here that the analytical solution, the difference, this y here, is actually my difference between the analytical solution and the numerical one. And you see that there is a gradual increase here. And it's not exactly, this difference is not exactly 0. And that's because my error goes like delta t squared. If I make delta t smaller and smaller, you will see a better and better result. So your result will not be equal to the exact one, but you can get closer and closer by making delta t smaller and smaller. What you also see when you look at the equations here, the results, is that obviously the acceleration decreases because you have a drag force, an air resistance, which acts against the gravitational constant. So that means that your acceleration decreases, but you also see that your velocity, when you look at the 4th column here, the velocity keeps increasing, right? You're acquiring speed, which is obvious. So what we are seeing here is what we would expect, right? Now, you can now see the final result. So the error is roughly at the endpoint is 0.002. What I've done here was to plot the exact value, the analytical one, and the numerical one. And on this graph, it's difficult to see the difference. That's why it's so useful to print the difference. So if I make now the spacing, the time spacing, a little bit larger, so the time spacing which I've decided upon becomes a parameter in your modeling. So if we now decide to say that delta t is 0.1, so we make it larger, and then we rerun, now you see a much larger difference, right? So you are starting to differ much more with respect to the analytical solution. And you see that when you look at the 3rd column of the printed value, where you have the, in this column here, you have the difference between the analytical and the numerical one. So keep this in mind. The numerical solution is an approximation to the continuous solution. And it will depend on the way you discretize your variables. So the finer you make the integration domain, the better your result will normally be. You cannot make it smaller and smaller because at a certain point, you will lose numerical precision. And then you will start to accumulate numerical errors, which can be pretty dangerous, actually. There are many cases of people not having been aware of numerical errors, which have led to catastrophes. So the reason why I'm putting some emphasis on this, what you might call, well, you could almost call it a trivial case, is that the basic operations which I have exposed here, these are those which we are going to see again and again and again. So everything we're going to do is going to be a kind of perturbation or addition to what you have here. But coming back to what we discussed last week about you analyzing the problem. When you have analyzed the problem, you found the forces. And with the forces, you have an expression for the acceleration. And that's the one you integrate up in these equations. Any questions so far? Does it sound okay? I'm hoping it's not too boring, but these are kind of elements which are important to put in place when we now are going to look at more complicated and what we might call more interesting systems and more realistic systems. So what I actually wanted to do now is to bring up another example. So here we did one dimension. And now you can guess what's the next move. So we move to 2 dimensions, right? So let's see what these equations look like in 2 dimensions. But now we're going to change the velocity and the drag force so that the drag force depends only on the velocity, not the velocity squared. So this is pretty well developed in the text of Taylor, and some of the exercises are actually dealing with the approximations to the theoretical answer we're going to develop now. So let's switch over to the whiteboard and slow down the pace a little bit. So let's bring up the whiteboard. So what we are going to do now is to look at the simple change of the problem we have here. And we are going to look at a problem now in 2 dimensions. So we are going to have an object falling in 2 dimensions, but it's now falling at a slower speed, at a lower speed, which means that we are going to assume that the drag force depends only on the velocity, not the velocity squared. So now we need to define again a system, and we are going to have y, positive y going upwards, and positive x going eastward in this case here. And the problem which we have is, so this is our coordinate system, and we are going to have an object which is now falling in here, and it may go up or it may go down. So if it's going up, there's going to be a drag force in the opposite direction here. So there will be an FD here. So depending on the kind of motion we have, we are going to have now either a drag force which points downwards or drag force which points upwards. So that's always against the motion here. So this will depend a little bit on your initial conditions also, and which kind of direction you're looking at. Let's now assume that the system has a vector, a velocity, and this is going to be given by a v of x times I plus a v of vy times j. So I and j are the unit vectors, and we know that if we choose a Cartesian system, these 2 guys are orthogonal to each other. So that means that I times j is equal to 0, and these are unit vectors. So we need an initial velocity. We need to specify that, and we need an initial position. And this initial velocity is something which we are going to write in a more compact way, like a v0 of x. And then we do the same with the y component. So it has a velocity in the x and the y direction, and we simply call this v0y. Then clearly, if we have an initial velocity, we also have an initial position. So we would then have a y and x. And we call this y0 and x0 at t0. And it's pretty common to put t0 equal to 0. That simplifies life a lot. Then what we have now is that we have a force F of D, and this is just a model for the force, which depends on the mass of the object, and there's a constant gamma, and then we have V here. So I actually have pulled out the mass. So in a certain sense, I put in a constant here, which is not directly proportional to the mass, but I've scaled it with the mass of the object, because then I can just divide by the mass here, and I have just one constant. So it means also that the net force, so if we take also the acceleration here, if we now define the downward directions as the negative y value, so this is going to be given by mg times j. And then if we now look at the force here in this drag force, that is obviously given by m times gamma, and then I'm going to have a v of x times I plus v of y times j. And here I have suppressed the time dependence of velocity, of just plain laziness from my side. But v, it depends on velocity, and vx depends on on time, and vy depends also on time. Does that sound clear? So this is our analysis phase. We have found the forces, and now we're going to solve the equations. So the net force is obviously the sum in this case. If we neglect all other forces, is going to be given by Fd plus g. And the acceleration in the x direction is going to be given by dv of x of dt. The acceleration in the y direction is going to be given by dvy and dt. So if I now look at my expressions here, the acceleration in the x direction is now going to be given by if we look at the expression we have for the force, this is given by minus n times y multiplied with v of x. And this is divided by n. So if I put n here, that means that my acceleration now is simply given by ax equal to minus gamma times v of x. And this is equal to dv of x dt. I can now do the same with the acceleration in the y direction. So I have now minus gamma v of y. I have divided by the mass of the object. So I have only the gravitational acceleration. So that gives me minus g here. And that is equal to dv of y of dt. Then finally, I have new equations. So I have that v of x is actually the derivative of dx with respect to time, and vy is the derivative of y with respect to time. Now, if you look at these equations here, there are some interesting mathematical properties which give us a hint that we may be able to solve the equations analytically. So also pay attention to the following. We are in 2 dimensions, and now we have 4 coupled differential equations. So every new dimension brings in, since we have taken a second order differential equation, which is the acceleration given by the second derivative of position, we have rewritten that in terms of 2 coupled differential equations. And then when we go to 2 dimensions, we get 4 coupled differential equations, okay? And you see that here, because that's what we need to solve. But there is an interesting mathematical feature here, which I want you to observe, which may hint at why you can solve this analytically. So take a look at these equations which you have here, and think a little bit about the mathematical form. Can you say something about the x and the y dependence here of these equations? Yeah? They are separated. Excellent. So when you see an equation like this, that these equations here, in the equations for x, there is no y dependence. In the equations for y, there is no x dependence. That hints normally to the fact that we can actually solve these equations analytically. In homework number 3, we are going to look at the velocity or the drag force as a function of velocity squared. So let me just give you that as a small digression here before we look at the analytical solution of these equations. So if you get something like this, where there is only an x dependence in the x direction, no y dependence, we say that these are decoupled differential equations. And that allows us to separate the solutions. So we would have one solution in the x direction, which doesn't know anything about the y direction, and one in the y direction, which doesn't know anything about the x direction. So what we call these are, they are coupled differential equations, but this specific case here, which we have, so the x and the y degrees of freedom are decoupled. So x and y degrees of freedom are decoupled. Normally, that's a very strong hint that if we can find the right trick, we will be able to find an analytical solution. So this often leads to possible analytical solutions. So pay attention to this kind of structure of the equations, because many of the manipulations which have been done in classical mechanics, and this is since Newton's time, so we have a body of exercises which have been developed over 400 years without the possibility to calculate numerically, where you actually have to find the right mathematical transformation in order to find the analytical solution. So when Kepler, Newton, and all these other people solved the gravitational equations, they made a transformation to spherical coordinates. And then suddenly they could actually solve the equations analytically. This is something which we are going to do a little bit later in this course here. So when we come to the gravitational forces and we are going to model the Earth-Sun dynamics, you will see then that we can actually obtain analytical solutions with some smart transformations. So the thing which is interesting for us now, since we have this feature, is that we can actually find a possible analytical solution. Now, on the other hand, so this is another digression, in homework number 3, there what we have is that Fd is given by a constant times the velocity times the absolute value of the velocity. In 2 dimensions, this is going to give us an equation which cannot be solved analytically. And you will see why. Because the force in 2 dimension here, in 2 dim, then this F of D is going to be equal to minus D times Vx times I. And then it's going to contain plus Vy times J and multiplied with the absolute value, which is actually Vx squared plus Vy squared. So that's a little bit uglier. And when you now set up the equation for the velocity and the acceleration in the x direction, for instance, so if you take the acceleration in the x direction, what you will have then is an equation which goes like this, minus d times v of x. But now suddenly you see that you have a dependence on the velocity in the y direction. And then we say that these are no longer decoupled. And in the next homework, you will actually have to solve this numerically. But if you do it in 1 dimension only, there is no, for v of x, there is no v of I. And that means that then you can solve it numerically, as we did last week. So just be careful with this kind of small subtleties. In some cases, you can find a nice analytical solution, and in others, you cannot. So what we're going to do now, before we move on, is take up questions if things are unclear, something which you'd like to ask about. Either if you are online, you can put in questions in the chat, unmute yourself, or you guys sitting here, feel free to ask questions if things are unclear. Because else what we're going to do now is to find the solution for this two-dimensional problem when we have a drag force which depends only on the velocity. So we are going to repeat now, unless you guys have some questions. We are going to repeat the same thing we did last Friday and last Wednesday, but now we are going to integrate up these equations here. And these equations, since they are decoupled, we can find the analytical expression for the velocity in the x direction and the same for the y direction. So let's try to do that. So these equations are not that difficult. And it's very nice to compare that with the numerical code as well, because you have analytical solutions. So let's take the equation for the velocity in the x direction. So we have a dv of x of dt, which is simply equal now to this constant minus gamma multiplied with v of x. And again, what we do now is that we separate out the velocity part on one side and time on the other side, and we integrate them up separately. So that means that what we do next is simply to rewrite this equation here. So we would have a dvx divided by v of x, and this is equal to minus gamma of dt. And then the next thing we do now is to integrate up from v0 of x, which we defined, to a final v of x. And now we put a dvx prime divided by vx prime. And that's equal to minus gamma. And now we put time t0 to 0. That's a little bit handier than dt prime. So this one is simply minus gamma times t. So anyone who remembers the integral which we have for the velocity? This is also a famous function, which you will see again and again here. And it's also one of the exercises in Taylor for this week. Anyone who remembers that particular function? If we integrate the left-hand side, there's a famous function which is 1 over x, if you integrate that, or 1 over variable v of x, yeah? Yes, the natural logarithm. Thanks, guys. So if I do that, this simply gives me ln v of x divided by ln v0 of x. And I want to have an expression for v. So what I do now is I take the exponential of both sides. And that means that what I get then is that I have v of x divided by v0 of x is equal to e to the minus gamma times t. So that means that my v of x here as a function of time is simply v0 of x multiplied with e minus gamma of t. So there is an exponential decay of the velocity here. So at a certain point, it comes to rest, as we would expect. We start with an initial velocity in the x direction, and then suddenly this object comes to rest. Okay, so we can do the same thing with the position, because we know that we have dx of dt is equal to v of x, so which is v0 x of e minus gamma of t. So I can now integrate up again and get the position. So that means that what I would have now is d of x, and I would integrate from x0 to a final x. And this is given by an integral from 0 up to t. And then I have v0x e minus gamma times t multiplied with dt prime here. And if I do that, then I get my final position here in the x direction. So I'm just integrating this up. And what I get then is I get an x of t, which is equal to x0 plus, and when I do the integration, I have to divide by gamma here. And then I get 1 minus e minus gamma of t. In one of the exercises this week, and I think it's exercise 3 or 4, I don't remember which one, you're actually going to look at the Taylor expansion of the exponential function. And then you can see what happens depending on the value of this parameter gamma. So how fast the velocity in the x direction goes to 0, and how quickly it will actually come to rest in the x direction. that will depend on this parameter gamma. So that's a small manipulation which you will need to do in one of the exercises. Any questions so far, guys? So what we can do next now, since we have everything in the x direction, so we have the velocity, we have the position, is that we can do the same exercise in the y direction. And this is a similar integral. It's a little bit uglier because we have the gravitational acceleration, but it's no more difficult than what you have seen till now. So if we do that, if we now take and integrate take the motion in the y direction, what we would have then is a dvy of dt, which is equal to minus gamma v of y minus g. So this is the original expression for the acceleration in the y direction. So this is our a or y here. And now we do the same trick. We isolate velocity on one side and time on the other side. So what we get then is just an equation which runs like this. We're going to have a dvy minus gamma v of y. We can actually change it to a nicer one. We can just take plus g here, and then we have minus dt. And then we integrate up. We take a v0y up to v of y, and we have a dvy of plus this gamma vy plus g, and this is equal to minus from time 0 up to t of dt. And this is just minus t here, which we have seen before. And what we could have done also is to multiply away this constant gamma. So that means that we would have a g divided by a gamma. So let us manipulate it a little bit more. So what I'm going to do now is to multiply with the gamma in both the numerator and the denominator. So what we will be getting then is a simplified expression here. So I got rid of this parameter gamma. So I would have a dvy, and then I would have a vy plus g divided by gamma. And this is equal to minus gamma times t. Everybody fine with that? I'm just getting rid of a constant here. So then this function as well is actually a log function. It's an ln function when we integrate it up. And this is something which we can just look up in mathematical formula, or you can use Mathematica, or you can use symbolic Python, and then find the analytical solution. So it's up to you which kind of tool you want to use in the analytical work. Is that too much freedom? So solving scientific problems means solving them with all possible means. Okay? So think of, that's the kind of way we want you to think when you're looking at a scientific problem. Because you have a bag of tools, which is quite impressive. I didn't have that bag of tools when I was a student. We were forced to solve everything analytically. And we were never given the formula for the integral. So we actually had to cook up the integral. So I spent, in a physics exam of 6 hours back in Norway, we could spend an hour on an integral. There's not much physics in solving an integral in a physics exam, right? So we want you to focus on the physics, and then you solve physics problems with all the available tools. We do not subtract points in the exercises if you use Mathematica in order to solve an integral. Keep that in mind, eh? So you can then integrate this one. And if you integrate it, this is a natural log again. So if you look at the function which we're going to integrate, it's actually not that different. It's actually the function which you saw here. We go up a little bit. It's actually this one, where the denominator just has the variable plus a constant. So it means that we're going to get an ln function again. So when we integrate up here, what we get is an ln of v of y plus this gamma g divided by gamma. And this has now a denominator where we have v0 of y plus g divided by gamma. and this is equal to minus gamma times t. And now we take the exponential of both sides. So we get rid of the log function, the natural logarithm. So what we have then is simply v of y plus g divided by gamma, v0y plus g divided by gamma, and that's equal. So this should actually have a minus sign here. I forgot that one, sorry guys. And this is e to the minus gamma times t. And then I can rewrite it. And what we are going to get then is something which now is going to contain these variables. So if we just shuffle over things, we will have a vy of t, which is going to be given by a minus g divided by gamma. I multiply on both sides with this quantity here. So this is going to be plus, oops, sorry. It's going to have a plus, and then I will have a v0y plus g divided by gamma multiplied with e of minus gamma of t. So that's my velocity. Then when I want the position, I can integrate up once more. And then we are basically done. We have solved the problem. So in this case, since we are in 2 dimensions, we get 4 coupled differential equations. So we have to solve 4 integrals. If we were in 3 dimensions, we would have 6 integrals to solve. But you see the basic pattern here, right? So the solution then, if I now look at the next step, which is dy dt is equal to vy of t, I would now integrate up again. So I would get a y0 up to the final y dy, and that will be equal to voy of t of dt from 0 to the final time t. And now I'm just going to be horribly lazy. I'm just going to give you the answer, because again, there's not so much insight in solving an integral. So we're just going to give you the answer here so that you can compare that with what you will get yourself. So that means that y of t is going to be equal to y0 minus g times t divided by gamma plus a v0 of y plus g divided by gamma multiplied with 1 minus e minus gamma of t. So this is the exercise we can do by paper and pencil. Now, the thing which is going to be interesting for us now is when we want to set this in to a code. So there are 2 small things which we need to think of. So when we go numerical now, and we are going to pick this up a little bit more again on Wednesday, because this becomes important in connection with the exercises 5 and 6, which you have in this homework, but also in the homework number 3. So if we do the numerical approach, what we could do now is to define arrays for v of x, v of y, x, and y. So we would then define 4 arrays. There's nothing which hinders you from doing that. And normally, what I recommend when you're writing your first program for these things, do it like that. It's going to give you a longer code, but it's more transparent. It's easier to see what we are doing. So I always tend to say, use the simplest possible approach. I have the velocity in the x direction, the velocity in the y direction. I need x and y, so that will define 4 arrays, which depend on time. So in our case, this means that all these quantities will depend on some discretized time. So this depends on time, So they're going to be all one-dimensional arrays, or vectors as we call them. But now you could make things a little bit more compact. So this is normally what I would call the brute force approach. Or if you don't like the word brute force, you could just say the straightforward approach. However, we can make this more compact when we use NumPy's way to represent 2-dimensional and 3-dimensional objects. So that can sometimes make the code much more compact and also a little bit more efficient from the point of view of what we call vectorization. It becomes less transparent. And in the beginning, people get a little bit confused. So you need to choose a little bit here. If you feel pretty strong in Python programming, you could use the more compact way of doing it. Or if you're less confident, just do the straightforward approach, which means that you would define arrays for all the variables which you have present. And I see that my time is running over. This is always so fun that I forget about time. So I have to keep an eye on time, guys. Sorry, yeah, we're just on time. This is to be continued. So the next episode of this season continues on Wednesday. And then we are going to look at other examples related to the homeworks and also other examples of forces. And then next week, we are going to dig a little bit deeper into conservation laws, which are perhaps for some of you, the more new things. These are things which you have seen probably before, right? And as I said in the beginning, I hope you don't get offended if we are looking at this boring falling objects, okay? Okay, guys, we stop here. Any questions? I'm gonna stop the recording here for everybody.